We're now going to finish up the rest of the notes on Lewis dot structures, and this will conclude with the examples of exceptions to the Lewis dot structures, or the octet rule, I should say. Before we get to exceptions to the octet rule, I wanted to get to a term called resonant structures. You might have heard me use the term before because we had an example of it earlier. A resonant structure is one of two or more Lewis structures for a single molecule that cannot be represented accurately by only one Lewis dot structure. Example of that on computer right there is ozone, O3. By the way, the plus and minus are just the formal charge, positive one, negative one. But this is ozone is O3, oxygen, 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 double bond with one oxygen, single bond with the second or last oxygen, you can say. Now, who said this first one had to be a double bond and a single bond of the last oxygen? Why can't it be single bond of the first oxygen and double bond with the last oxygen instead of double single bond and a single double? In a way, it's kind of the same, but it isn't. This is not the same as this, but it kind of is the same. There's a term for it that there's more than two or more Lewis structures for a molecule that cannot be represented accurately by only one structure. In other words, it's saying there's more than one way to draw the Lewis dot structure correctly. And most of the time, we're really just talking about like rotating your single, double, maybe a triple bond, okay? But that's primarily what the difference is. So these two are resonant structures of each other. Resonant structures is of another thing. So it's kind of like saying one person isn't a twin. If someone has a twin, one person isn't a twin. They're twins of each other. This is a resonant structure of this molecule. They're both O3, and they have kind of the same Lewis dot structures, but they're not. These are two different Lewis structures representing the same molecule, O3. Okay, so if I want to draw the Lewis dot structure of carbonate ions, there's three different ways of doing it. I'll just show it all to you right now. Here are the three different resonance structures. I could have carbon double bond on one oxygen and single bond on the other two, like here. Carbon double bond on the left oxygen or carbon double bond on the right oxygen. Either way, they're all correct. It's just where do you want to put that double bond? On the bottom oxygen, the one on the left, on the right? But so you notice it's the same, but they're not the same. The term is called resonant structures. That there's more than one way to draw the Lewis dot structure correctly. So, okay, so that's the term resonant structures. Now let's get to exceptions to the octet rule. Let's start with the easiest example of exception to octet rule. That is incomplete octet. Beryllium hydride, BeH2. Beryllium is a group 2 element, hydrogen's group 1. Beryllium's a group 2, hydrogen's group 1, so a total of 4 electrons. Now, I don't know how in the world you're going to share 4 electrons so everything has 8. Obviously, that's not possible, okay? But here, notice, each hydrogen has 2. Each hydrogen has 2 electrons, hydrogen has 2. And, oh well, that's going to be exception. In fact, if you found the formal charge of beryllium, beryllium's a group 2 element, group 2 minus 0 dots, 2 lines, the formal charge of beryllium is 0. And formal charge of hydrogen is 0. So in a way, this is the best and only Lewis dot structure of this, and that's just how it is. It's an incomplete octet. Usually, incomplete octets are usually if group where the center element, like beryllium, is a group 2 or 3 element. But that doesn't have to be the only case, but many times, the incomplete octet includes elements like beryllium being a group 2 element, group 2, group 3A elements being the center element. Many times they will be incomplete octets. Doesn't mean it will have to be. Okay, BF3, boron trifluoride. Boron is a group 3 element. Boron's a group 3 element. Here's the Lewis dot structure. Notice that this boron only has 2, 4, 6 electrons. It only has 2, 4, 6 electrons. It does not have 8. In case you're wondering, why not make a double bond? You could make a double bond here. Okay, move those 2 dots, make a double bond there. But then boron will have 8. However, formal charges. Boron's group 3 is 0 dots, 3 lines as in this picture. Boron has a formal charge of 0. if I made a double bond there, then boron would be a group 3 element. Group minus dots minus lines is formal charge. 3 minus 0 minus 4, the formal charge of boron would be -1, and the formal charge of fluorine here would be +1. This thing has all formal charges 0. This is the best structure. So that is the best structure in that molecule. Okay, so now let's look at other examples of exceptions to the octet rule. So again, boron is going to be exception there. Okay, and we're going to next chapter, which will be starting not too long from now, will be the shape of the molecules. Notice this is linear. There's going to be a name for this. It's going to be called trigonoplanar, but we'll get to that later. Odd numbers of electrons. Nitrogen's group 5, oxygen's group 6. Now, you start sharing electrons, 11 electrons, so everything has 8. It's impossible if it's odd numbers. It's kind of like if you were given 11 socks and you're supposed to pair them up, or 11 shoes, left, right shoes, whatever, and you're supposed to pair it up. Well, that's not possible if you have an odd number. And oh well, there's no way you can mathematically do odd number of electrons to pair it up so everything has 8, or even have, just pair them up. It's just not possible. That nitrogen there just has 7 dots. Nitrogen's a group 5 element, 3 dots, 2 lines. This formal charge is 0. Oxygen is also formal charge 0. Group 6, 4 dots, 2 lines. The formal charge of that is also 0. Okay, so the last type of exceptions octet rule is called the expanded octet. That's where the center atom, usually this applies for center atoms where the principal quantum number is greater than 2, meaning the third row on the periodic table. This does not mean if it's the third row on the periodic table, it will be an exception. It can be. Just because it can be does not mean it will be an exception. SF6, sulfur is the center, surrounded by 6 fluorines. Well, they have to at least be single bonded. Otherwise, it's not part of the molecule. It's not connected. So in this case, notice sulfur has, 2, 4, 6, 8, 10, 12 electrons. Right? Every line has 2 electrons. 2, 4, 6, 8, 10, 12 electrons. And, that's just how it is. Sulfur is group 6 elements, 0 dots, 6 lines. Formal charge of sulfur is 0. Formal charge of every fluorine is 0. So that is the best Lewis dot structure. And so remember, we do formal charges if there's more than one way to do it. And even if it doesn't look like the most accurate way, the best structure is the one that has no formal charges. That's how we did formal charges, or a smaller set of formal charges if you cannot get 0. Okay, so these are just exceptions to rule, exceptions to octet rule. If it's odd number, or if it's a group 2 or 3 element as a center, many times there are exceptions. Or expanded octet is if it's a principal quantum number greater than 2, period 3 on the periodic table, row 3 in the periodic table, or greater. It does not mean it has to be, but sometimes it can be exceptions octet. In case you're also wondering, nitrogen monoxide, NO, or nitrogen monoxide, does that really exist? Yes, nitrogen monoxide gas, this reddish orange gas, does form in nature. So just say nitrogen monoxide, yes, it does form in nature, even though the Lewis dot structure of this thing does not seem to fill the octet rule in general. Okay, so these are just examples of exceptions octet rule, and we also did formal charges. Not formal charges, resonance structures. That's it for chapter 9 notes. We are going to go on to chapter 10, which is molecular geometry.